There. Okay, recording started. Let's go. So thank you everyone for joining us today for this seminar from the winners of the Tomorrow's Mathematicians Today conference. My name is James. I'm hosting this seminar today, and I'm part of the Early Career Mathematicians Committee for the IMA. Which, if you're on YouTube, that is the channel that you found yourself on. So if you enjoy, please like and subscribe. So a little bit about the Early Career Mathematicians Committee. What we do is try and advocate for events and opportunities for early career mathematicians. And that starts at undergraduate level and goes all the way through until, maybe postdoc, if you've spent some time in industry early on in your career, things like that. And we try and put on events that will interest you, if that is who you are. Our events span from things like this seminar to virtual maths teas, which you can find on the IMA website. We've done conferences in the past. We're trying to do more like workshops and upskilling. So please have a look on the IMA website. Keep your eyes peeled for the work that we do if you think it's interesting, and hopefully see you at a future event. So today, I'm very fortunate to be joined by Mingjia and Andi, who both will tell you about why they won some awards at this Tomorrow's Mathematicians Today conference. This is a, so far, yearly conference run by Greenwich. It's very easy to see what goes on. If you just Google the name, you'll find the conference. It's for undergraduate students to present work that they've done in a project or maybe in research, opportunities over summer, and then at the conference, there are two awards. There is now let me get this right before I get it wrong. There is the IMA Popular Prize, Popular Vote Prize, and IMA Prize for the Best Presentation. So you'll see roughly what those were in the upcoming session. So we will start with Mingjia, and I'm going to give the bio that is on the website. So she recently graduated with an MSci maths degree from Imperial. Her research interest in maths broadly and widely spread across fluid dynamics, geometric mechanics, dynamical systems, soft condensed matters, and electromagnetism. In particular, she's very keen in studying chaotic and active dynamical systems with dissipation in maths and physics using geometric mechanics and differential geometry, such as many various pendulum dynamics, active matters in biomathematics, liquid crystals, and a variety of MHD theory and models. And I'm sure she's going to tell you about her PhD position that she just got and how that's going to be incorporated in there. So her fun fact, she's obsessed with collecting different types of CDs and albums in pop music. So if you also have this passion, her LinkedIn is on the website. So, go and have a chat if you like. She has a whole 3-layer shelf dedicated to all of her CDs, and she probably has over 100 now, possibly more at the time that anyone else is listening to this. She also loves to review different places that she's been to, like cafes and restaurants, and write reviews on Google Maps. She almost has 400 followers, which is, as she says, quite unbelievable. So, Mingjia, please introduce your talk and the prize that you won and anything else you would like, and then the floor is yours.
Yeah, sure, of course. So I attended the Tomorrow's Mathematicians Today 2024 this March, and it was a really, really interesting and pleasant experience, and I really enjoyed it. So it was a good opportunity for undergraduate students to present their own work and also to see other undergraduates at different universities across the UK and to listen to other people's research interests, which is a very nice opportunity if you are very, very keen into mathematics. So I won the IMA Popular Vote Prize, which I was really, really grateful for, and I really appreciate it as well. In my talk at the TMT event, I mainly talked about geometric mechanics in soft matter with examples in liquid crystals. And today, what I will be talking about will also be the study of geometric mechanics, but in a compound dynamical system. And we will see soon in the talk what exactly that means. So this talk is actually part of my final year research project. So I hope it will be somewhat interesting and useful to some of you. The title of my talk is Lagrangian reduction by symmetry and semidirect product structures in compound dynamical systems. So I guess many of us have more or less some exposure to classical mechanics during our undergraduate study. And classical mechanics is everywhere. It appears in sports, for example, when you're playing basketball, the minute you throw the ball out of your hands, its motions or its trajectories over time can be studied using classical mechanics. It may also appear in your grandparents' house, their old pendulum clock, for example. And we know pendulum is a very classic mechanical model with rich applications. All those examples I mentioned are rather simple dynamical systems. And we love simple things because we then have simple ways to deal with them. However, things are not always as simple as just a flying basketball. And in fact, in nature especially, most things are not simple at all. And they are quite complicated to understand. And some of them we call compound dynamical systems, where each degree of freedom evolves in the frame of motion of the previous one, and each one having their own dynamics from the change of frame. And their behaviors over time are rather difficult to predict using simple tricks from classical mechanics. The calculations that we need to do may be very long and very involved. Then someone may be put off by thinking, oh boy, what I'm gonna do? I want to know the dynamics, but I don't want to make my life much harder. But don't you worry, we're mathematicians. We are trained to find better and better solution, no matter how tricky the problem is. And we are really good at it. So from a new perspective, we use the study of geometric mechanics, independent of the choice of coordinate systems, and in the language of Lie group and Lie algebra, to solve the complicated mechanics, including the compound or the hybrid dynamical systems. One of the key ingredients in our recipe is symmetry, and symmetry is described by Lie group. And for people not familiar with Lie group theory, don't worry, we will get to that in a second. And we know there are Lagrangian and Hamiltonian pictures in classical mechanics. And same here, in our geometric approach, we start from the Lagrangian side, and we aim to simplify or to reduce the dynamics using symmetries in the system by a method called Lagrangian reduction by symmetry. And then passing to the Hamiltonian side, we will see a special structure called semidirect product structure arising from the Hamiltonian equations. And all of those topics will be captured first by a theoretical demonstration, and then by an elegant example in the talk. So one of the motivations of my talk is the first sentence here. Nature is organized by skill and symmetry. These two things basically characterize all of the physics around the world we live in. And today, our main focus will be on symmetry. This important concept is one of the main building blocks in geometric mechanics. And it was made clear until 1918 by Emmy Noether in her celebrated Noether's theorem, stating that every continuous or every differentiable symmetry has a corresponding conservation law in conservative systems. And this has laid a solid foundation of the more symmetry-focused theme in modern physics. A very simple example to think about would be the free rotation of the sphere. The sphere rotates around the vertical axis in the absence of gravity. And in this example, each degree of freedom evolves separately in their own frame of reference. They do not talk to each other. And the rotational sphere has a rotational symmetry, which is described by the Lie group SO3, the rotation group. And now, what if we spice up the setting with some twist? Imagine spheres within spheres or worlds within worlds, where big worlds have little worlds that feed on their velocity, and little worlds have lesser worlds, so on to viscosity. So this is the poem by Louis Richardson describing turbulence. And here's a nice picture I found online, which is exactly what the poem is saying. And speaking of symmetry, what if there are some other parameters that break the symmetry? What does that mean? Does that mean we just lose all the nice properties and we are no longer able to analyze the dynamics? Well, intuitively speaking, no, it shouldn't be and cannot be the case. But math is way beyond intuition. So we need rigorous proofs and arguments to back up our theory. And symmetry breaking is an important and common phenomenon in math and physics. Here, I divide it into two different cases, one in finite dimension and the other in infinite dimension. A finite dimensional symmetry breaking example would be the heavy top dynamics, where gravity here kicks in and breaks the rotational symmetry of the spinning top with a fixed point of rotation. And in infinite dimension, symmetry breaking is often seen in fluid dynamics. And for people who've been wondering what exactly is a compound dynamical system, so here I have two examples, two pictures, and hopefully they will give you a better idea as to what a compound dynamical system is in reality. Also, one in finite dimension and the other in infinite dimension. So for the picture on the left, it shows a rotation of an elastic spherical pendulum or an elastic Foucault pendulum mounted onto a rotating turntable. This system is compound, and because here all degrees of freedom, they talk to each other, they evolve, they interact with each other. The pendulum dynamics become much more involved and much more complicated due to the presence of the 2D turntable rotation. So the pendulum oscillation will be affected by the additional external rotating frame. And for the picture on the right, it shows a wave current interaction system, which is also compound. So we see the tides producing trains of curved wavefront expanding into the sea. And for wave current interaction, we model the sea surface motion by decomposing the surface dynamics into a two-dimensional horizontal flow map representing the transport by current, acting on a one-dimensional flow map, which represents wavy-like motion of surface elevation. So it describes the dynamics of how the horizontal fluid flow acts on the wavy vertical oscillatory surface elevation, just like currents acts on waves. As promised before, I want to quickly go through some terminology and notations that we will be using later on in the talk. So first, a Lie group is a group of transformations that depend smoothly on a set of parameters. A Lie group has a group action, which can be either from the left or from the right. A left Lie group action on a configuration manifold can be denoted by concatenation. And similar here, for a right Lie group action, we just have the group element G acting from the right of Q. A Lie group has a corresponding Lie algebra, and a Lie algebra is a vector space with a special bracket called Lie bracket that is bilinear, skew-symmetric, and satisfies the Jacobi identity. And the action of the Lie algebra on a dual vector space can also be denoted by concatenation. We can also view a Lie algebra as being isomorphic to the tangent space of the Lie group evaluated at the identity. So this is another way to define what a Lie algebra is. And here are definitions of infinitesimal transformation and Lie derivative. Don't worry, you don't really have to know what they are. So I put them here because later on, we will be using the notation of Lie derivative in some calculations. As you can see, there are some similarities between these two definitions, and indeed, a Lie derivative is one type of infinitesimal transformation. And also here, still, don't worry if you haven't seen them before or you don't really know what that means. That won't stop you from following the rest of the talk. So because at the end of the day, we would like to write our equations on the dual of the Lie algebra. And the reason for this will become clear in the next few slides. And in order to do so, we need operations that will give us elements that are dual to the Lie algebra. And luckily here, these two operations, the diamond operator and the coadjoint operation, will do the job. So they are two mappings that pair elements in different spaces and eventually yield elements that are dual to the Lie algebra. So far, so good. So now let's get into the technical bit. So we start from the Lagrangian. And we consider a Lagrangian that is written on this product space, where Tg1 and Tg2 are two tangent spaces of two different Lie groups, G1 and G2. And V star is a vector space. Just as what we do in classical mechanics, we then apply Hamilton's principle to our Lagrangian with 5 degrees of freedom. And the dot here denotes time derivative. And capital theta naught here is a vector space quantity that is the advected quantity, which is a fixed element in the vector space. The advected quantity remains invariant under the flow. So it is carried along by the flow from an initial point at an initial time to a current point at a current time. Its physical properties will remain invariant. So a very interesting example for me to illustrate, to better interpret what the advected quantity is to think of traveling on the plane. And now it is the perfect time because now it's summer vacation time. So when you are booking your summer holiday destination and when you are traveling on the plane, you are advected or carried by the plane from the airport to the destination. During the flight, the essential properties of yourself, say your height, your weight, will not change. Well, given that you don't eat too much on the plane. So that's what I mean by advected quantity. And for our method called Lagrangian reduction by symmetry, well, because we've been talking about symmetry over and over for such a long time, so now it is time to really use the symmetry in the systems to help us solve the problems. And the idea behind is inspired by Henri Poincaré in his famous 1901 paper, in which he said, equations of mechanics can be cast into a new form on the dual of any arbitrary Lie algebra, which may be interesting to know. Well, obviously, he was being way too modest, because ever since then, a considerable amount of literature has sprung, and thanks to the pioneering works by authors like Jerry Marsden, Alan Weinstein, Tudorato, Darrell Holmes, etc., now we have a systematic way to do Lagrangian reduction by symmetry, called Euler-Poincaré reduction theorem. It works perfectly well in many single scale and single symmetry systems. And now we would like to know, how does this reduction theorem apply in practice for our case, specifically speaking? Because now we're dealing with compound dynamical systems with multisymmetries. So idea is that we assume the Lagrangian is invariant under the right composed Lie group actions, so we can reduce it stage by stage, each stage using different symmetries in different groups. So here, the first stage, we use symmetry in the second Lie group, G2, and this group action, G2 inverse from the right, will only be acting on 3 variables, G2, G2 dot, and capital theta naught, while G1 and G1 dot will be left untouched. And then the next stage, we apply the symmetry in the first Lie group, G1, and this group action, G1 inverse from the right, will be acting on all the variables in one go. This gives us a fully reduced Lagrangian small l with only 3 degrees of freedom, where u1 and u2 are two different velocities describing different parts of the motion, and they are Lie algebra valued variables. And capital theta is the vector quantity that lives in the vector space. And then by a reduced Legendre transform, we can get to the Hamiltonian side and have a reduced Hamiltonian with 3 degrees of freedom as well. Here, m1 and m2 are the conjugate variables to u1 and u2. And capital theta, because it is a vector quantity, so it appears in both the Lagrangian and the Hamiltonian. And then the equations on the Hamiltonian side, or we call the Lie-Poisson equations, written on the dual of the special structure semidirect product Lie algebra, can be cast into a more compact matrix form, where the matrix operator on the right-hand side defines a Lie-Poisson bracket. And remember the form of the matrix operator, as we will see something quite similar very soon. So here is a beautiful picture of northern lights. So I don't know how many of you have either saw the news or actually witnessed the northern lights in the sky a couple of months ago this year. I did remember seeing pictures all over my social media. So you probably are wondering, why do we care about this? Well, that's because the northern lights, auroras, neons, all those phenomena are closely related to the Alfvén waves, which is a type of MHD waves that propagate along the magnetic field lines. And because we just demonstrated our method theoretically, so now it is a perfect time to find some examples that will back up our theory. And here, we particularly interested in the 2D Alfvén wave turbulence because it is a compound dynamical system that can be studied using the geometric mechanical formulation that we just derived. So for the planar Alfvén wave turbulence dynamics, we also first start from the Lagrangian side, and we consider its dynamics taking place on this product space, where G1 and G2 are two different Lie groups, each describing the fluid and the magnetic part of the motion. And capital V star here is the vector space that contains the vector quantity, which is carried by the ideal fluid flow. And now let's apply our reduction scheme by symmetry. So still stage by stage. The first stage, we apply symmetry in the second Lie group, G2, and this group action G2 inverse from the right will only be hitting 3 variables as before, G2, G2 dot, and capital A naught, while G1 and G1 dot will not be affected this time. And then the second stage, we apply symmetry in the first Lie group G1, and this group action G1 inverse from the right will be acting on all of the variables in one go, as before. And this gives us a fully reduced Lagrangian small l with 3 variables, where u1 and u2 are 2 different velocities, each describing the fluid and the magnetic motions, respectively. And capital A is a fixed element, which represents the vector potential of the magnetic field. And how they are defined, these 3 variables, are characterized by different colors here. By a variational principle, we can calculate the equations of motion, and they will take the following form, as in equation 0.11. And then by a reduced Legendre transform, we get to the Hamiltonian side with a fully reduced Hamiltonian. Still, m1 and m2 are the conjugate momenta to u1 and u2. And because A is the vector quantity, so A appears in both the Hamiltonian and the Lagrangian. And this is an explicit Hamiltonian adapted from the paper by my supervisor, Darrell Holm. It has 3 variables, 3 degrees of freedom, where omega here is the potential vorticity 2 form, and chi is the charge particle density deviation from equilibrium, and A is the vector potential of the field. So the construction we have in mind is that we want an ideal fluid flow carrying a magnetic field with a vector potential that is sequentially interacting with the charged particle density, which also exerts feedbacks to the magnetic field, as it is also being carried along by the ideal fluid flow. And same here on the dual of the semidirect product Lie algebra, which looks exactly the same as in the general methodology part. Our Hamiltonian equations, aka the Lie-Poisson equations, can also be written into a compact matrix form, where the matrix operator on the right-hand side denotes a Lie-Poisson bracket. And because here we are in 2 dimensions, so the algebra action are represented by the Jacobian operator, capital J. So to wrap up the talk, we hope to draw some conclusion. The first is that based on and motivated by previous work, we have extended and developed a coordinate frame and operational scheme in geometry mechanics that help us to deal with the complicated mechanical systems with single or multi-symmetries. So that captures the dynamics of the compound or the hybrid systems as well. And we have successfully reduced the number of degrees of freedom that we need to worry about. And the second thing is that we chose the 2D alpha wave turbulence equations, particularly as an example, because they exhibit Hamiltonian dynamics similar to the general semidirect product Hamiltonian structure. And finally, the finite dimensional examples provides us very useful insight as to the infinite dimensional cases. So it helps us to better understand what to expect and what may happen for the infinite dimensional examples. So for example, the rigid body dynamics in finite dimension has a good implication to the infinite dimensional fluid dynamics. Because say the Lie group in rigid body will be the rotational group SO3, while the Lie group in fluid would be the diffeomorphism group. And the group action in rigid body case is matrix multiplication, while the group action in fluid dynamics would be the composition of smooth invertible maps. So that's the end of my talk. I hope it will be interesting to some of you, and thank you all very much for listening. And yeah, here are some references that I used throughout the talk. Should I stop screen sharing or?
You can keep it for now, just in case there are any questions and you can quickly flick through. So thank you very much for this very thorough and rigorous talk. It's quite clear there is this, framework to take objects like Lie algebras, which are obviously a very pure tool, but are being reimagined in this applied setting. So I have questions, of course. Does anyone else want to pipe up with questions? I'm happy to go first while people think or type. So how do you, now that you've got these system of equations, how would you actually solve them? Like, I imagine analytically might be a challenge, but numerically, what would you do? Because it's coordinate free, and most of the time, numerical things need a coordinate to be able to discretize. So how would you go about doing that?
Oh, yes, of course. So I will say here, myself is not an expert in numerics, but the equations can be solved in numeric because the so-called coordinate frame is that it doesn't really depend on, say, the choice of Cartesian coordinates or spherical polar coordinates or cylindrical coordinates. So when you are doing numerics, for example, I don't know if I can go back to the slides. Say if you want to analyze the dynamics of the pendulum, you just choose whichever coordinate that works best for you. So say if you think, the spatial coordinates, the X, Y, Z, Cartesian coordinates works best in the set of equations, you can use that into your numerical implication, and then carry on the programming, the coding. Or in some other cases, well, if you think the body coordinates would be more useful, would be easier, you can then go on to use the body coordinates or the spherical polar coordinates. But sometimes, you need to take care of potential singularity that will appear in the equations. So which system of coordinates you want to choose also depends on which will give you more accurate results, considering there is a singularity in your system.
And do you have a good example of when like a singularity has appeared?
Yes. So also back to the pendulum case, the pendulum example here. So for its rotation or for its dynamics without the turntable, hanging straight down, the vertical downward position is actually a singularity in the pendulum dynamics. So here, the azimuthal angle phi, as you can see in the picture, I don't know if you can see there's a small phi at the bottom of the turntable. Yes, so this angle will be undefined, and the pendulum, when it swings back to the vertically downward position, it may just jump, or it may produce some stepwise precession patterns, as you see in the Foucault pendulum in a museum or somewhere. So this position is a singularity, or some people call it monodromy in algebraic geometry. So yes, you need to really think about how to deal with the position when the pendulum is just hanging straight down, or when it swings back to the original vertically downward position.
And these singularities, how do they appear in the equations? How would you know, like if you calculated the whatever you've just done for the pendulum, the coordinate free system, do you have an intuition about what could cause a singularity, or would you need to impose a coordinate system before you see the singularity occur?
Well, so for a pendulum dynamics without the turntable, I think it was way beyond the development of geometric mechanics, because it's like maybe hundreds years before in classical mechanics, people realized that it is a problem when the pendulum goes back to the originally straight hanging down position, and this is a singularity in the system. So I would say detecting the singularity would be a different story. So you need other tools for you to know where the singularity is, and then if you know its potential behavior, you can carry on the analysis and to say, well, where the pendulum might behave in long term, and how can we capture, or how can we calculate and predict the dynamics using our equations.
Yep, makes sense. Okay, I'll stop pushing on that point. My other question is, in the Alphen example, you said that like G1 and G2 were the fluid and the fluid, the magnetic dynamics. How did you come up with that? Is that because of like prior knowledge about the Alphen wave turbulence? Like, is that what that comes with, like domain knowledge?
Yeah.
Okay.
So a more comes from the physics side.
And what happens if like you were doing the physics and you didn't realize that like magnetic dynamics was important? What would happen here? Would it just give you a bad model, or like would there be something else going on?
I wouldn't necessarily say that people would not realize the presence of the magnetic part, because also the Alphen wave is like a very classic topic in the study of MHD. So we have enough prior knowledge, like background knowledge to know what might happen in this setting. And also, if I can go back here. So the model adapted from this paper, for example, it was like 30 or 40 years back, and people at that time have already been studying what is going on in the alpha wave. Well, I would say a lot of MHD models, you realize there are two parts. There is fluid part and a magnetic part, but how they exactly act on each other, or like how do they interact with each other, would be a important question to really think about. Like you really need to think of the group action. So the fluid acting on the magnetic part, or the fluid acting on some other vector space with order parameters or with advective quantities, and then the whole thing acting on the magnetic part. I would say this probably takes a couple of tries to see which would work. And then you really need to do the calculations, because I feel like for geometric mechanics, this is not like something that can be simply shown to people. This is something you need to do. Say you really need to do the calculation or work out the examples.
And where are those calculations? Like, where would you, I guess the question is sort of comes into where this model is developed, but yeah, where do those calculations appear? In which parts would you do that?
Okay, so for example, if you have a Hamiltonian here, or if you have a Lagrangian, I think a Lagrangian will be easier to say. Yes, so here, for example, you have your reduced Lagrangian with 3 variables, and then you put them into a variational principle and take the variation. So say you have the integral, and then you invoke the Hamilton's principle, and you calculate the variation with respect to each variable in your Lagrangian, and you can derive the equations of motion.
Yep.
Like, yes, I don't know if I include an explicit example, or maybe, yes, like I did here. So you have the equations of motion for your 3 variables, U1, U2, and capital A here.
Yeah, so in there, the different scenarios or the different models that you'd be creating would feature in the this infinitesimal derivative with the L, with the Lagrangian, or would it feature in the adjoint operator or this diamond operator, or both?
Mm-hmm.
What would you say?
Both, because this equation is kind of like a main structure for you to expect what will appear in your equations. So here, because we have 2 velocity, so it looks a little bit more complicated. But imagine you just have 1 velocity. So your equations of motion will only have the first line, and on the right-hand side of your equation, without the second term at star U2. So you know you will have the at star U1 with dl by du1 plus dl by dA diamond A. And your second equation will not appear because you don't have the second velocity. And then your third equation will just be the time derivative of this advective quantity. And on the right-hand side will just be the Lie derivative of the velocity u with A. And this is actually similar, or it is the Euler's equation in fluid dynamics, where you have the time derivative of your autoparameter, and the right-hand side is what people call the div, the divergence of that parameter.
Yep. Very good. So in light of time, we can move on to Andi. So thank you very much again for the presentation and the fantastic questions. Yeah, thank you very much.
No problem. Thank you for having me. And thank you for your questions. They are very good questions and very valuable.
One thing I can definitely do is find questions to ask.
And you did a good job.
Thank you.
Okay, I'll stop sharing.
Yes, please. Okay, Andi, would you like to start sharing your screen?
I will indeed.
Fab. Okay, so our second talk of this session is from Andi. Andi is a recent master's graduate from Warwick, has a particular interest in applied maths, including epidemiology and dynamical systems, which I believe we'll be hearing about today. Outside of maths, he's a diehard Arsenal fan and plays football where he can. So please feel free to put that in the comments, however you want. So Andi, tell us about what you won and your talk, and the floor is all yours.
Yeah, so at the IMA TMT 2024 conference, I was shortlisted for and then won the prize for the best presentation. If anyone stumbled across this and is wondering whether they should join that conference, it really was great. It's accessible to all levels of undergraduates and even beyond. And the quality of talks was amazing throughout, and I was extremely grateful to have won the prize for best presentation. I spoke a little bit there on my master's project, which I'll also be speaking about now, and that's the complex relationship between deprivation and disease. The talk I'm giving today is a slight adaptation of that, maybe slightly more advanced, and I'm hoping we'll touch on more points, but should follow the same key elements and should hopefully, yet again, be accessible to all, but if not, questions and I'll try to fill in the blanks where I can. So if I can cast everyone's minds back, I know they don't want to, but to 2020 and the COVID pandemic, we very quickly realized that age was a risk factor with COVID. The most elderly in society were disproportionately affected compared to other members of society, and we very quickly realized that these the most elderly needed to be protected the most, and we could see that clearly, and then that was reflected in then the models we made and the decisions that were taken. How can we protect the most elderly? But then the natural question to ask is, okay, age is a risk factor, but what other risk factors are there? And so I'll quickly just show you what's on the screen now is two maps, both of England and London, and they're side by side because one is grading the areas of England by deprivation, so how they rank on the deprivation decile, with the darker areas being the most deprived areas of England, and then the same areas ranked by their death rates. Now the scale's not quite the same because they're being measured in slightly different ways, but you can see that there's some real hotspots of deprivation that also ended up being impacted and had severely high death rates from COVID. And then this sort of finding was repeated multiple times. This is a Office for National Statistics publication, and it showed that in a lot of the early months of COVID especially, the death rate among the most deprived was more than double that of the least deprived in society. And then again, I'll just show you another quick graph of the death rate per 100,000 in the different quintiles of deprivation, where quintile 1 is the most deprived in England. And you can again see this trend where the most deprived in society have a higher death rate. So then the natural line of thinking is, okay, if age was a risk factor and age was included in our modeling and how we thought about the disease, why wasn't deprivation? And then that was sort of the motivation behind and the reason behind my project and what I'm going to be speaking to you a bit about today. So we've already covered the motivation. Just to make sure everyone's on a level footing for what comes next, I'm going to briefly introduce SIR models. It should be straightforward, so it should be brief. And then we can look at how we could potentially expand those models to include deprivation and how those elements link together. But also we'll talk about the available data sets and how they sort of force our hand in the models whether we're able to create. And then that leads into the challenges and limitations of everything involved in what I'm talking about. So let's start very basic. Why do we even bother modeling diseases? And it's because we want to predict outcomes. What's the final size of an epidemic? How long will it take? How many infections or deaths will there be? And when will the peak of the epidemic occur? These were very important questions that were addressed and were the driving force behind lots of the decisions made in the coronavirus pandemic. but they're applicable to a range of diseases. And if we can accurately, or with relative accuracy, get an idea of these sorts of things, they can help inform policy decisions, such as should we go into lockdown, or should we just sort of let the disease tow its course. And then once we have these models, if we're able to do that and then decide, okay, we do need to take action, we can then use these models to assess the effectiveness of different policy decisions. So if we vaccinate, would it be better to start by vaccinating the most vulnerable in society? Or would it be best to just vaccinate whoever first comes, first served sort of thing? So it's, can you then adapt those models to see which ways of tackling the disease are best? So what do these sort of models look like? So you got the most basic one that you can get on the board, and this is called an SIR model, which stands for susceptible, infected, and recovered. So the population is split into those three different groups: those that haven't been infected, those that currently have the infection, and those that had the infection and have now recovered from it. And there's two key parameters within that model. There's our force of infection beta, which controls the probability of a successful infection given an interaction between somebody who's susceptible to the disease and somebody who has that disease. And then we also have this parameter gamma, which controls the rate of recovery once someone has been infected. And then these sorts of graphs on the right is the sort of output that you would get from numerically running this system over a period of time. And you can see clearly, you know, we can see those outcomes that were of interest previously, like peak of the epidemic, the outbreak duration, the total number of infected, and that's the sort of things that we can derive from those graphs. But as we spoke about earlier, age was of particular interest. So how would we adapt these equations to include age? Now, this is where it gets slightly more complicated. So I'd like everyone to briefly imagine the population of England is split into three age groups. We have children, we have working class individuals, and we have the elderly. So now, instead of just having one population where everyone is treated the same, we sort of have three of these systems running concurrently and at the same time, which slightly complicates matters because, and I think that's highlighted best in the example of if our population had no infected individuals, the disease would just die down. It would completely die off. There would be no new infections. Now, however, if we consider our three different populations of different ages, we could have absolutely no infections in a singular age group, but the disease wouldn't die out because infection could be brought in from another age group and an interaction there. So we not only have to care about the interactions between an age group population, but how they also impact each other and how they interact. So it's sort of like we've got three sets of these equations. It's almost not that simple because these three sets of equations are now impacting each other. And we need to capture that. And the way that we do is through a mixing matrix, which is the Cij in the equations here. And that sort of denotes and encapsulates the probability of interactions between our different age groups. Now, if that was a bit too much, we're going to be circling back to that idea in a couple of slides. So don't worry, and hopefully it should be made a bit more concretely. But those are the sorts of ideas that I wanted to build upon now that we're thinking about deprivation. So a nice place to start was to look at, okay, what's already been done? Like, what are the sort of building blocks we have to start with? And there were three particular papers of interest, which I've listed up here in case anyone else finds them of interest. And they sort of show the start of what I wanted to continue. Now, this first paper looked at the most basic SIR model that we discussed and thought about how can we incorporate social determinants and include the R0 value, but sort of stop there in a one-dimensional system without stratification and that sort of thing. So I wanted to take that a step further and think, okay, how can we stratify by age, deprivation, and so incorporate everything into one. So then the second paper became of interest, which was on the creation of generalized contact matrices like we discussed before. But this time, can we create a contact matrix that goes beyond one dimension? So not just different contacts between age groups, but maybe different contacts between age groups and deprivation quintiles, for example, which is what I wanted to use. And then finally, we had this last paper, which sort of brought everything together and was a great deal of inspiration. And that was the introduction of social mixing between deprivation groups in a model which also incorporated age stratification. So this is the exact sort of thing that I wanted to do. They didn't really use real world data though, so I wanted to see how far can I take it and sort of what fruits do we bear from that. So yeah, to summarize, with deprivation in mind, I wanted to build upon existing models to create one that was capable of handling extensions by 2 dimensions simultaneously, so that's age and deprivation at the same time, to see can we incorporate this deprivation risk factor somehow. And then I wanted to fit these models to the available data. And then part of the original reason I signed up for the IMA TMT and why I'm giving a talk now was to communicate these findings in a high level and accessible way. And if we can find a way to successfully include this deprivation, you know, the benefits could be tenfold. We could, in a similar way to why we'd want to predict outcomes of the disease I spoke about earlier, if we can successfully incorporate this, it could be a great way to ease the burden of diseases in the future on the most vulnerable in society. So with that in mind, we had to extend our basic SIR system. So we're going to start with we're going to start by talking about the data we had available first of all. We measured deprivation in England using the English indices of deprivation, which I spoke about before. It takes a weighted average of the 7 areas you see on the screen and then gives each area a ranking from 1 to however many areas there are. And then the worst scoring 10% get put into decile 1, and the best scoring 10% get put into decile 10, and the best scoring 10% are the least deprived. I then combine those areas to create quintiles, which is what I then used in my stratification in my model. It was also important to think about, I was looking at death as a burden of the disease. So it's also important to discuss what sort of death data we had available. Daily death data was all collated by ONS, but obviously there was that delay in reporting, you might remember at the time, just because of the delays in registering deaths and that sorts of things. But then deaths by deprivation were presented in each decile and presented monthly, and it was a similar sort of thing for age, which was really a sort of struggle because it really restricted the amount of data available. And that obviously, as we'll speak about later, has a knock-on effects on the type of things that you can do, because data is really the driving force behind this. So let's start with the baseline model. We started with our basic SIR model, and with the dynamics of COVID in mind, we sort of expanded this to include 2 new areas, which were pre-symptomatic infectious and asymptomatic infectious. And the reason behind that was because it was driven by real-world data and the real-world effects of COVID. Most people did get were asymptomatic infectious. They did not have any symptoms, so we needed to include that into our model, but there was also an incubation period. So we included that, and then obviously with that comes the choice that you can make with regards to parameter values. Do asymptomatic individuals recover quicker? Are they less infectious? And those sorts of decisions. And you can now see in our tree, we have loads of different transmission branches, and then from each different type of infection that can occur, how likely is it to occur? So a symptomatic infectious individual should be more likely to infect someone than someone showing no symptoms. And can we incorporate that into our parameters? And then, you know, the recovery rate similarly. So that was our baseline model, but we cared about deprivation. So first, we expanded this to an age stratified model. So if you didn't quite get what I was going on about before, hopefully this diagram, whilst complicated, should make it slightly more clear. Instead of just one singular set of equations, we now have 3 running simultaneously. But as you can see, a symptomatic infectious individual can now impact the other sets of equations. And so they're all interlinked, and they're all having an impact on each other. and then that ultimately changes the amount of infections that occur, the amount of susceptibles we have. It just sort of messes with the whole thing. So we needed our contact matrix to measure the interactions between the different age groups. And there's a really interesting plugin in R called Polymod, which is based on a study. And this sort of shows the contact matrix we have on the right. It's a nice visualization. The lighter the square, the more interactions that occur. And we can see that in each age group, the most interactions occur with individuals within the same age group. But especially for those of a working age, you know, they have a lot of interactions with younger adults and the elderly too. And then sort of you get that flip dynamic with the elderly and the youngest, where really the majority of their contacts are focused within their own age group. Okay, but then we sort of need to imagine that we've got this 3-leveled system, but I wanted to include deprivation quintiles, and there's 5 of them. So you sort of have to imagine also extending this out 5 different ways as well. So you sort of end up with a whole bunch of systems. So the mixing matrices, I will show, sort of highlight how complicated this really did get. So first, we need to sort of discuss the fact that there was no real empirical data that discussed mixing between different deprivation groups. And again, that's a limitation that I'll maybe discuss a little bit later. But with that in mind, we sort of had to guesstimate and think about what the best mixing matrix would look like for age and deprivation. And that led to the consideration of 3 different scenarios. The one is random mixing, where everyone within each deprivation quintile interacts with each other equally. So someone in a most deprived area is equally as likely to encounter someone in an individual from a least deprived area as they are someone in a most deprived area. I think I kind of butchered that a bit, but essentially, if someone in the most deprived area is equally as likely to meet someone from any of the other deprivation quintiles. And that's the sort of contact matrix that it creates. And you can see it's pretty much the exact same contact matrix it should be, because deprivation is in effect having no effect because it's completely random and it's an equal probability across the board. So that's a good baseline to check that our model is actually doing the correct thing, because it should be giving us the same output. And then there's the other extreme, which is absolutely no mixing between the deprivation groups. So someone in the most deprived areas would only ever interact with somebody else in the most deprived areas. And that's what gives us these distinct lines within the contact matrix, because there's absolutely no interaction occurring outside of individuals within the same class. And then there's the last scenario, which is probably more aligned to real life, which is this assortative mixing idea. This idea that you're more likely to mix with individuals within the same deprivation quintile, but it's not concrete. You can also interact with individuals from other areas, but with a lesser probability. And that creates this sort of effect where it sort of peters out, but there is mixing between all the groups. Yeah. So then once we had created all of those, we needed to assess the effectiveness. But before that, here's a quick summary of all the models in case that was a bit too fast for you. This baseline model on the left just shows, you might see a big square and think, what's that big square for? It's just to highlight that everyone is mixing equally because there's just one group. There can be no mixing between groups if there's only one group. So now that we have a sort of summary of all of our models involved, we then needed to figure out some of the parameter values, because you had to sort of guess the best values based on publications, and sometimes it was just a guess. You just had to guess based on reported figures from hospitals and stuff, like the percentage of asymptomatic versus symptomatic individuals and that sort of stuff. So we had to fit our models, which means we had to use the data available and use methods to try and find the best value for that parameter based on the data that we have. And one of the methods of fitting that I use, I'll just speak about quickly, is Markov chain Monte Carlo. And I'll quickly summarize this because I'm not the best expert. And if anyone's a better expert, they can sort of clarify at the end. But the way I think about this is it's a best guess machine. We have a guess for the distribution of a parameter. And then given that guess, we sort of draw a random sample from that distribution of what our parameter could be. We then compare it to our initial starting belief and see if it has a higher log likelihood value. So essentially, can it be better maximized using our new value? And if it can, we sort of shift our distribution and go, okay, that was sort of better. So let's increase our mean or decrease our mean. And then that's now our new prior belief. Let's take another guess and see what happens. And so sort of you repeat that often, and then that sort of drives and you get a distribution of all of the accepted values, and then that drives your decision of the parameter value to use. So I'll quickly show you some of the output that was produced from all of this. Some of it was good, some of it was bad, some of it worked perfectly, some of it didn't. In this case, you can see a really rather pretty looking graph that in some cases really does follow the shape of the observed deaths. And these were using a variety of different fitting methods. These were used, it was, for example, with two-parameter Markov chain Monte Carlo, and you can see that we are capturing that peak of the disease, but maybe in some parts we are overestimating it. And then we can see the breakdown when we start looking at the quintiles in our age and deprivation model. Again, the output is not that great because we just didn't have as much data to work with. So it sort of ends up being more blocky, and then you lose that sort of growth and decrease in deaths. So now that we've discussed all of the output, it's worth noting what this could be used for, as I touched upon before. If we can continue to expand this, and I'll talk about how we can expand this, it could have loads of applications in real life in lowering the disproportional impact on the most deprived in society, which is obviously a great benefit. But then you think about these sorts of models and policy implementations. Can you even take it a step further beyond disease modeling and think about, if we are to implement a different sort of policy, how would it impact these groups of individuals? So just to note quickly on things that we missed out on, there's probably a lot of missing data. If we didn't mitigate against it, there was sort of a decision taken that we would sort of brush past it, but it's those sorts of ideas that the most deprived in society may have not reported a positive COVID test because they couldn't afford the time off work and that sort of thing. So there are individuals that will have fallen through the gaps, or the data that wouldn't have been reported, and we didn't try to mitigate against this. And there's a lot of uncertainty in the parameter values. So can we include and fit even more parameters? And then can we investigate further waves of the disease and how lockdown perhaps affected different the different groups differently, in the sense that lockdown could have an effect on the most deprived in society that only shifts the parameter value slightly, but with the least deprived a lot, or vice versa. Sort of what's the uptake, I guess, in the policy decisions. And then this last idea is about the ideal data set, and the fact that there was no mixing between age and deprivation reported. So we sort of had to give the best guess, and that deaths were only really reported monthly for the deprivation quintiles. So we really do need to think about what data is the best to have and how can that drive forward our models. But then there's this really important question, that is it actually possible to create this data set? Because there's a really interesting study which I've linked the author of there, and it states that the more identifying features you put in a survey or a questionnaire, the chance of re-identification increases exponentially. I think it's like, I think it was 9, but don't quote me on that. If only 9 identifying features are asked, there's a 99.9% chance of re-identifying the individual who filled out that survey. And so that's obviously a big worry among the most vulnerable in society who may already have a distrust of the health system and the authorities. So thank you for listening. I'll end there and I'll open the floor to any questions.
Thank you very much, Andy.
Thanks.
I have questions, of course. So you're very fortunate to know that this is work that I have worked in. I also did COVID modeling during the pandemic. So I have thousands of
There
questions.
you go.
But Mingjia, would you like to ask any questions before I absolutely go for it?
Yeah, sure. I actually do have a question.
Go ahead.
So it's more about your SIR model. So, yes, please, if you can go back to
This one?
the one before. I think the previous two slides,
Oh,
perhaps,
the
where
very,
you had you have the equation. I'm just wondering because I saw the equations and I just did like a calculation very quick in my mind. So if you just add everything on the left-hand side and everything on the right-hand side, and you will see the right-hand side is 0. And does that imply the, say, like the time derivative of these three, or maybe more because you have the I running from the index, maybe from 1 to n, for example? Are these variables adding up together to be a constant of the motion? And what does that imply? Can it help you to eliminate variables, I guess?
It's a brilliant question. I'll show you the more complicated version of those equations at the end. And it's so this is just a full set. If you add these all up, these will all total 0. And basically, we've split the entire population into one of these categories. So when we add them all up and that totals 0, that's telling us that the total population is unchanging, which
Yes.
if
Oh, okay.
in my case is okay because we're looking at 3 or 4 months, so we're not expecting huge changes in the population, the population of England. It won't change massively, so that's an okay assumption to make. If we're talking more longer term, 20, 30 years, probably that shouldn't happen because there might be a slightly more significant shift.
I see. So this, say this particularly works well within a relatively short period of time where your total
Yeah.
population will not have like big fluctuation.
For sure, yeah, because then it's
Okay.
yeah. It is worth noting it does help you solve them in smaller cases if you are trying to solve them by hand. It's a neat trick, especially with the simple SIR models, to get the numerical sort of output by hand. You sort of use that trick, so it's a nice observation.
Yeah, that makes sense.
It's a good question.
Thank you. Thank you very much. Yes, go ahead, James.
My time.
Yeah, it's your time.
So I have a couple of questions which I think would help the other people in the audience, because I know the answers. But if we go and have a look at the mixing matrix, we see that it's not symmetric.
This one here, yeah.
Yeah, like why is that?
You know, this is something that I struggled to sort of wrap my head around too. It's sort of like you have you sort of take I think it's a weighted average, and sort of there are different amounts of interactions within each group, and then that sort of gives you this skew symmetry. You sort of I do get what you mean, because you expect it to be symmetrical, but it doesn't quite work that way, in the sense that these individuals will just have more total. So if we talk about the working class, for example, they'll just have more total interactions than the other classes, and that's what sort of drives it.
Yeah, so like the way I interpret what you're saying is, because you've got, in the 65 plus category, there could be people, there's lots of people in that who may be interacting with those who are 0 to 18. But if you take the other way around, so let's say all of the 65 plus have contacts with 0 to 18s, but not necessarily all 0 to 18s have contacts with 65 plus.
Yeah.
And that's where this skew symmetry could come from. Does that sound reasonable.
Yeah, it's sort of like if you take your child to daycare, they're going to interact with hundreds of other children, but they only got one set of grandparents, sort of
Yeah,
thing.
yeah. Nice. Polymod's a really nice survey, actually. I really
Yeah.
I enjoy reading the paper, and you take enjoy as you want. But there was a one done as well during the pandemic by was it? Oh no, I think it was by the London School called Comics. That was done throughout the pandemic. So are you going to continue with this work, or are you now like going
So,
where?
this was my master's project. I've hung it up and I've left it with my supervisor. I'm not sort of continuing in academia. It, I sort of took that decision at the beginning of my master's year because I didn't think I'd want to, and then by the end of it, I was like, well, maybe
Oh,
it wouldn't have been the worst
right.
thing, but never say never, and the door is open in the future.
Good. It's really, I mean, at least the way I see it, there's a lot of nice open questions that have come about from COVID. So, I think if you were, the door is always open, particularly at
Yeah,
Warwick. Warwick is a very big institution on infectious diseases.
for sure.
On one of the first slides, there was this deprivation and death mirroring across England. And I noticed that in London, it was sort of opposite. Do you mind going back to that slide? Right, I think it's right at the beginning.
Yeah, I'll go this one. It's sort of layered over the top of each other. This one right here.
This one, yeah. So like you can see in England that there are these, particularly in like the northwest. I think that might be
Yeah,
like, I don't know where that is.
it's,
I'm
it's,
terrible at
it's
geography.
Liverpool sort of
Yeah,
area, I think.
yeah. Also the northeast is also like similar. But in London, you see that like take the center of London. On the right, it's really dark, and on the no, sorry, on the left it's really dark, and on the right it's really not dark,
Yeah,
which is like a complete opposite to the narrative of that deprivation was correlated with death rate. So from what I think is that London is a separate entity in itself. But what do you think is causing this?
but I think it is important to note that London always seems to be the exception. Um, it's sort of there's things going on in London that don't really match everything else. And I think because this is not concrete, this is just my view. I think just because of the nature of London, that there was maybe lockdown was less restrictive in a sense that there was sort of more uniform movement across the capital, which resulted in a more uniform spread. It's also worth noting, and I think it describes it a little bit. On the left, um, we're talking about. I think it was a really large range. I think the scores ranged from like 0 to 900, and on the right, the death rates were sort of. It was a little bit of a different scale, so they're a little bit closer together, which sort of makes it seem like they're all one color. So there's definitely an effect there. I think part of it is caused by the fact that it's just London and there was more uniform mixing, and part of it is also just the scale of things throws the colors off a bit.
Yeah, I did know that during the pandemic, a lot of people who lived in London also just left, which could cause
Yeah,
problems with,
true.
if you're talking about deprivation, because deprivation would have been calculated before the pandemic. So then all the
Yeah,
people, there was a lot of people who sort of left London because they can. That may also be
that-
influencing this a little bit.
yeah.
Um,
It's a very good point, and it's one that I hadn't thought about because yeah, it was measured from their perceived home address. So
mm.
if they had an address in the London borough, they were classified based on the deprivation quintile of that borough. So if they then went somewhere else, it sort of messes with things, but there's no real way to combat that.
Yeah, absolutely not. This is just how reality and data is. That brings me on to my next question, though, which is with the deprivation scores, how did you, in your SIR models, how did you decide the number of people in the deprivations for each of those compartments?
It's a really good question, and you just sort of I assumed uniform spread. I think in the sense that I took so for example, if there are let's use small numbers, 100 people in deprivation quintile 1, and then we know there's 200 people total, it's spreading that equally based on the proportion of each age group, if that makes sense.
Yeah,
So
fair enough.
if the first age group makes up 25% of your population, they take 25% of that number, and then so you think 20 people that took me far longer than it should have. 20 people in quintile 1 from that age group, and then continuing like that.
Yeah, I mean, the only way to get this information would be to do like a polymod study on deprivation, which doesn't
Yeah.
seem like likely to be on the agenda for a while, which is
No.
obviously crucial to what you're suggesting here.
Yeah, for
And
sure.
you know, obvious that we should probably try and understand the contacts between deprivations and things. So yeah. I would have probably just done uniform as well. There might be some interesting data from like the census might help a little bit with this potentially.
I think it did. I think the census was also used in parts. I think it was used when the age groupings were unclear. I think I used uniform, but then the census informed where it could.
And I've got one final question. I won't ask you about the Monte Carlo stuff, the Bayesian stuff. You talk about deaths, and I notice it's not in the model. So how did you get from these pictures to the number of deaths?
Yeah, so I essentially, it's a good observation. It's a little function, and then we're fitting the probability of death. So we're taking the number of, we're assuming only deaths from symptomatic infectious individuals, and then we're taking a proportion of that, trying to include things like the lag time and other factors to determine the probability of death for each of these different groups. And so that was ultimately the main aim, was can we concretely show that the probability of death is shifting among these different deprivation quintiles and these age groups? And ultimately, yes, we could show that there was sort of a positive distribution. I don't want to use the word positive, but that
Yeah, I know what I mean.
the probability of death was the lowest among the least deprived and the highest among the most deprived.
So you put that function on the R compartment, then you ran the simulation, used the R compartment, and then
it would have been the I compartment rather than the R, but yes.
Yeah. So you take a proportion out of I.
Yes. And then also a proportion out of asymptomatic, and obviously those numbers differ. I think it was a far smaller number for asymptomatic, but just to try and capture everything.
Yeah.
I'm trying to remember off the top of my head how that proportion was calculated.
In reality, I mean, if you look with the death data, you can see that there were people dying outside of hospital from COVID, and these might be those who didn't want to say they had a COVID infection or something like that. So, like, asymptomatic here is playing a large role in that.
For sure, yeah.
People who are not saying they're symptomatic.
For sure,
so,
and that again circles back to the sort of slipping through the net. And
yeah,
if they don't report it, it sort of doesn't get picked up.
Yeah, exactly.
And it's just one of those natures of the data again.
Yeah. I'm at now out of questions. Well, I'm not, but I am. So, I guess I mean, thank you for answering the questions as well. And
thank you. They were great questions.
Yeah, sure. You should be very happy. Both of you should be very happy with the projects that you did and that high quality for where you are. So, yeah, well done. So on that note, I'm happy to end that if you're both happy to end.
Sweet. Thank you. It was great to give the talk. Thank you for the questions.
Thank you both for coming as well. I appreciate it, and enjoy the rest of your summer.
Thank you. You too.